Hello everyone, today in this video we are going to talk about electric field, and after this video you should be able to define what is electric field, and you should be able to find its unit and dimension, and you should be able to calculate the electric field due to a point charge. So we know a dog has its territory, and when you go to its territory this happens. That means in its territory dog is a boss. Similarly, a king also has a territory, that is his country, and inside the country he is king, but outside he is not the king, he is a normal man. So inside a territory someone or something is a boss or can show its power. Similarly, a charge also has a territory, and in its territory it can exert force on other charges. So suppose we have a small positive charge in the territory of this big positive charge, then the repulsion will happen. But if you keep this positive charge outside this territory, then nothing will happen. So inside the territory there will be force, outside there will be no force. So this territory is called electric field, and within this field the charge can exert force on other charges, but it cannot exert any force outside the territory, and this territory is called electric field. So electric field is a region around which a charge can exert force on other charges. And the next term related with electric field is electric field intensity. Suppose we have a charge called source charge. Source charge is a charge which produces electric field, and we keep a small charge called test charge to detect the electric field of this source charge, and there will be a force on this charge inside the electric field. So if I want to find the intensity of electric field at this point, then I have to divide the force at this point by the magnitude of test charge. So if you divide the force by magnitude of test charge, then this will give you the intensity of electric field at this point. So if you want to find electric field intensity at this point, you have to do the same thing. You have to divide the force on test charge at this point divide by the magnitude of test charge. So electric field intensity is equal to force by test charge, and we denote electric field intensity by E, and that is force by Q naught. And I'm writing Q naught because we are keeping test charge to test the electric field of this source charge. So the electric field intensity at any point due to a source charge is defined as the force per unit positive test charge placed at that point. So for different point we have different electric field. So source charge is the charge which produces electric field, and test charge is a small positive charge used to detect the electric field. And electric field intensity we have already discussed, and this is the formula for electric field intensity. Sometimes we called electric field only, so they are same thing. Electric field intensity or electric field is same. Unit of electric field, so for that I need formula. Now for unit I have to write the unit of force, that is Newton, and unit of charge, Coulomb. So Newton per Coulomb is the unit of electric field. For dimension, now for this we need the dimension of force and dimension of charge, and dimension of force is m1l1 t minus 2, and dimension of charge is at. So the final dimension is m1l1 t minus 3 a minus 1. So this t will go up and it will become minus 3, and this a will go up and become minus 1. So this is the final expression for dimension. So the test charge, that is Q naught, need to be very small, otherwise it will disturb the electric field due to the source charge. So let's see how. So this is the electric field, and if we keep a small test charge, this will move and this will not move. That means electric field will not be disturbed. But if you keep a very big test charge, then this charge would move, then you won't be able to find the electric field. So because this big charge is disturbing the electric field of this, so test charge has to be very small. And this is the exact expression for electric field. So electric field is force by charge, but we are putting limit. That means Q must be very small, and this expression is saying the same thing. That means Q naught should be very small, that it should be near to 0. So this expression means test charge should be very small so that it must not disturb the electric field of a source charge. And electric field intensity is a vector quantity and its direction is same as the direction of force. So this is the vector formula for electric field with cap. So force is also vector, electric field is also vector. So charge is not the vector, so I am not keeping the cap out here. And direction of electric field and force is same. So suppose this is the source charge, this is the test charge, then direction of force is in this direction and electric field will also be in this direction. Next is physical significance of electric field, that is importance. So it provides a way to characterize the electrical environment of the system. So by knowing the electric field we can characterize, we know what kind of surrounding a charge is having, and it tells the force experienced by a unit positive charge just at that particular point. So if we know the electric field at this point, it will be very easy for us to find the force on a test charge when we keep this in this point. And it tells the magnitude and direction of electric force. So by knowing the electric field we know everything about the electrostatic force. So now we will derive the electric field intensity due to a point charge, and sometimes we may call it electric field without saying intensity. Whether we say electric field or electric field intensity, it's kind of same thing. So we are considering two point charges. So one is source charge kept at O and this is test charge kept at point P. So R is the distance between them, and let F is the force on Q naught due to Q, and the direction of force is towards the right. And electric field is also towards the right. We already know the direction of force and electric field is same. So for the timing I'm giving the direction of electric field also. So we want to find the electric field at this point P. So this is the same diagram I have used, and I have written the same thing out here. So electrostatic force on Q naught due to Q at point P is given by this is Coulomb's law, and according to definition electric field at this point is given by force by Q naught. So this is the definition of electric field. Electric field is force per unit charge. Now I'll put the value of this force. This Q naught and this Q naught will get cancelled, so I'm left with this. So instead of this I can write K. So this is the final expression, E is equal to K Q by R square. So this expression is similar to that of Coulomb's law, only we don't have the test charge out here. So electric field produced by this, so this is the expression of is equal to K produced by a Q point charge at a distance R from it. And in vector form we can write this. Now out here you can see the electric field depends on charge as well as the distance. So if you increase the source charge, then electric field will increase, and if you increase the distance, the electric field will decrease, because it's square inverse law. So if you go far away, the electric field will decrease, and if you come near to the charge, the electric field will increase. So these are the factors affecting electric field at a point. It depends on strength of source charge and it depends on the distance from the test charge. So more the charge, more the electric field, more the distance, less the electric field. So this is the electric field versus distance graph. So when distance is very small, then you can see electric field is very high, and when you go far away, the electric field decreases and becomes zero at infinity. So out here you can see when R is zero, out here the electric field is infinite, because this line is become parallel, and when R reaches infinity, that side E is becoming zero. So electric field decreases when R increases. So you can try this question. You have to find the electric field at 5 mm from a charge of 10 microcoulomb. So using this formula you can find the electric field. E is equal to KQ by R square. So this is the next question. Calculate the electric field strength which is required to just support a water drop of mass 10 to the power minus 3 kg and having a charge of 1.6 into 10 to the power minus 19 coulomb. So this is the water drop. Force on water drop will be downward force, that is the weight. So in order to balance this, we have to give upward force F, and this should be electrostatic force. So out here these things are given. So downward force is weight. So formula for weight is mg. So if you put the values, you'll get 9.8 into 10 to the power minus 3 Newton is the downward force. Now to support the water, we need upward force is equal to downward force. So F is the upward force, W is the downward force. So we know electric field is force by charge. So out here force will be electric field into charge. So I can put force is equal to electric field into charge. So now if you take this Q down, you can easily find the electric field. So weight is this much and charge is this much. So if you solve this, you will get E is equal to 6.12 into 10 to the power 16 Newton per coulomb is the unit of electric field. So similarly you can try this question. So out here you have to find charge, not the electric field. Electric field is already given. Now let's understand what is the meaning of electric field. What does it mean? Suppose I have two regions. In this region I don't have any electric field, and out here I have electric field. I am denoting the electric field by these lines. So out here electric field is 0, out here it's not 0. Now if you place a positive charge, then in this region there will be no force, and here there will be a force. So in this region the charge would move, but when there is no electric field there will be no force. So similarly if you put a negative charge, out here the negative charge would move, but in the region where there is no electric field, charge would not move. Now these two charges are moving, that means there is another charge, that is the source charge in the surrounding, or the charge which is producing this electric field. So there must be a positive charge at this side, so that this charge is getting repelled and this charge is getting attracted. If there is an electric field, we should understand two things. If you leave a charge in a region with electric field, the charge would experience a force or it should move, and there must be a source charge nearby. So these are the two things you should understand. One, the other charges must experience a force and there must be a source charge nearby. Now let's summarize the video. So the region around a charge where it can exert force on other charges is called electric field, and this is the formula for electric field: force per unit test charge, and unit is Newton per coulomb, and this is the dimension. And this expression is indicating that the test charge must be very small, near to 0, otherwise the test charge would disturb the electric field of the source charge. This is the formula for electric field due to a point charge. If you increase the charge, electric field will increase, but if you increase the distance from the charge, then electric field will decrease. And electric field is a vector and its direction is same as the direction of force. So this is the end of the video. Please don't forget to like the video, and I would love to read your comments. Your comments will encourage me to make more videos. Please do write something on comment, and if you are new to channel, please subscribe the channel. And out here I'm giving my phone number. If you need help in any topic, you can WhatsApp me. Thank you.